I'd like to talk today a bit about, we'll just change of basis. I'm gonna do two examples of change of basis and talk a little bit about conceptually what's going on. So I'm gonna start with well, the matrix that we're changing the basis of is going to be the matrix 1, 3, 1, 2. And this is a regular old invertible matrix. It's actually quite obvious that it's invertible. You can sort of see at a glance that the rows and columns are linearly independent of each other. And then our change of basis matrix, which we'll call P, is going to be 1, 2, 2, 5. And this is not an arbitrary matrix, it's a special matrix. I picked it because the determinant of the matrix is 1. I picked a matrix with determinant 1 because when we find the inverse of a matrix, which we will be doing, you divide by the determinant, and so dividing by 1 is particularly easy. And it decreases the messiness of the inverse matrix. Well, I'll just do the first example. I'll just walk you through the computation. First, we find P inverse, which is 5, -2, -2, 1. So the way we find the inverse for a 2 by 2 matrix is you switch the entries along one diagonal, and you take the negatives of the entries across the other diagonal, and then you have to divide by the determinant, which in this case is 1, so you don't really actually have to carry out that division. And you can see that the product of these matrices is the identity matrix 1, 0, 0, 1. You can confirm that. So we have an invertible matrix P, and so to do the change of basis on A by P, we conjugate A by P, and that means you multiply PA P inverse, and we do that multiplication. We can do it in two ways. We could first multiply, PA and then P inverse. We get 1, 1, 3, 2, or first multiply AP inverse and then multiply that by P. But the result in both cases is the same, which is the transpose of A. However, this example doesn't really shed light on what is going on. It's just an algorithm. And now we'll do a second problem, but this time we'll do it with some more visualization and explanation as to what's going on. So over here we have our coordinate system, and then we have a vector in our coordinate system. We'll call the vector, well, that's 4, 1. So we could see that our vector 4, 1 is 4 times the yellow vector plus 1 times the orange vector. Now again, we're going to pick an invertible matrix, and this will serve the role of our change of basis matrix. This time I'll call it Q. But again, I'm going to pick a matrix with determinant 1, because that makes the inverse neater. So I'm going to use the matrix 2, 1, 3, 2 as my change of basis matrix, which we're going to call Q. And depicted here is the new basis. In blue we have the vector 2, 3, that basis vector, and in green we have the other basis vector 1, 2. And And these basis vectors are the columns of our matrix Q. We know our matrix has determinant 1, and you might know the determinant is the area of the parallelogram spanned by the basis vectors. Looking at this picture, you can find it believable that the area of this parallelogram is 1. And so the inverse is pretty easy to find. We just add negatives along this diagonal, and that gives us the matrix 2, -1, -3, 2. And now we could express our vector 4, 1 in terms of this new matrix Q. The idea is that 4, 1 will be some linear combination of the columns of Q, so that we'll have some vector x such that qx equals 4, 1. In order to find that, we multiply by Q inverse. So, as you can see, once we do the algebra, this gives us the equation x equals Q inverse 4, 1. And carrying out that computation, we get the vector 7, -10. Here's what that looks like geometrically. This is 7 times the blue vector minus 10 times the green vector, and that's equal to 4, 1. It's cut off a bit because it sort of goes off the screen, but the place where the blue and green meet is the point 14, 21. A fact that we know somewhere in the back of our heads is that a space has a basis, and every vector in the space is some linear combination of the basis vectors. But this fact becomes far more important when you think about the possibility of having an alternate basis of some other linearly independent vectors. The point of this discussion is that the same point of the plane has different coordinates depending on what our basis vectors are. A point worth noting is that our standard basis vectors have all zeros besides for a 1 in one of their spots, which corresponds to the identity matrix whose columns all have zeros besides for one entry with a 1 in it. And so in order to find the coordinates of a vector in the standard basis, you simply multiply that vector by the identity matrix to get that vector back. But this disguises the fact that a vector is a linear combination of the basis vectors. And now again, like we did with P, we can do the change of basis on A by Q. And that means we multiply QA Q inverse. And this gives us a new matrix, which turns out to be -18, 13, -29, 21. And unlike our first matrix, this matrix looks nothing like A. It's not at all obvious why we would call this matrix similar to A. But since we went through the whole process of interpreting the change of basis matrix Q, we can now understand this similar matrix in that context. When we're given a vector, we multiply by Q inverse, and that gives us the coordinates of that same point of space from the perspective of Q. Then we have A operate on the coordinates. This is similar to A because it's doing A's operation. Once we get the result from A, we multiply that by Q to interpret the result in terms of Q. To break this down, we are given a vector B, and we multiply that by Q inverse. This gives us the vector X, such that Qx equals B. We then have A operate on X to give us AX, some vector, and then we multiply by Q to get a new vector, B prime. This in some sense leaves A intact, except for the fact that it performs the operation of A on a vector the way that Q understands the vector. But afterwards, we undo this interpretation of the vector in terms of Q. And so, we've only temporarily switched the vector to the way that Q understands it in order to do the operation. So we would call this the change of basis on A by Q. It is the same linear operator A, except in that the operation is done in Q space. So before I go, I'd like to take a look at one worked example. Over here, we're going to be multiplying QA Q inverse by the vector 1, 1, which will give us -5, -8. Now let's look at this step by step. The first step is we multiply 1, 1 by q inverse. This gives us the vector 1 minus 1. This is the way you would express 1, 1 as a linear combination of the columns of q. Then we operate on 1, negative 1 by a. This gives us the vector negative 2, negative 1. This is simply the way that a operates on the q coordinates of 1, 1. Now that we have our resultant vector by a, we interpret it as a linear combination of the columns of q, taking negative twice the first column of q and negative once the second column of q gives us the vector negative 5, negative 8. In my next video, I plan on taking a closer look at this example, seeing what properties of a are preserved, why they're preserved, and then why we would care about such a change of basis.